Welcome to Section 5 of the Robert Shaw Uniline Division Fundamentals of Pneumatic Controls video training program. This section will provide a discussion on the operation and function of pneumatic relays and switches within a pneumatic control system. Previous sections of this program discuss control theory and the operation of other pneumatic controls and should be reviewed before proceeding with this section. The theories and applications discussed in this video series are generic in nature and can be applied to any pneumatic control system regardless of its manufacturer. Pneumatic relays and switches provide a great deal of flexibility in the application of the controllers within the mechanical system of a building. These devices provide the logic and switching sequences in the complex and advanced world of HVAC control systems. This section will cover each type of relay individually, discussing their applications, piping, and adjustments as necessary. The first device covered is the diverting relay. These are some of the diverting relays available. There are models available with adjustable set points as well as non-adjustable types. Also available is a signal comparison type diverting relay. The first device to look at is the adjustable set point diverting relay, which comes in a single-pole double-throw model and has the option of selecting a 0.3 or 3 PSIG switching differential. For this device to function properly, it must have a main air supply of 15 to 25 PSIG piped to its M or main air port. The primary function of this device is to convert a proportional pneumatic signal into a positive switching action at some predetermined setting. This is accomplished by changing the set point adjustment to a pressure setting between 3 and 20 PSIG. When the pressure at the signal port reaches and exceeds this setting, the relay switches. This closes and blocks the normally open port and opens the normally closed port to the common port. A common application for this device is a high limit control, as shown here. The diverting relay allows the mixed air controller to operate the outside air dampers until the signal from the outside air transmitter indicates the air temperature has exceeded the 70-degree setting. The relationship of output pressure and temperature at the transmitter is covered in the receiver controller and transmitter tape, Section 4, and should be reviewed if necessary. At this point, the relay switches, blocking the signal at the normally open port and exhausting the air from the dampers through the common to normally closed port. This causes the dampers to close to their minimum position. This relay could be used as a low limit by connecting the signal from the mixed air controller to the normally closed port instead of the normally open port. Then, as long as the outside air is above the set point, the normally closed port is connected to common. This is the signal comparison diverting relay. This device is non-adjustable and has a single-pole double-throw snap-acting output. It is designed for use in systems where the comparison of two proportional input signals is required to divert or block a signal. For this device to function properly, it must have a main air supply of 15 to 25 PSIG piped to its M port. In this example, the signal comparison relay is utilized to execute a changeover function based on enthalpy in an economizer system. As long as the signal on port S coming from the outside air enthalpy transmitter is equal to or lower than the input signal at S2 from the return air transmitter, the normally open port will be connected to common. The mixed air controller will then use outside air for free cooling. When the input signal at S is greater than the input signal at S2, the normally open port will be blocked. The common port is connected to the normally closed port, exhausting the air from the actuator, closing the outside air dampers, thus causing the system to recirculate return air. This device is a non-adjustable diverting relay. It is a snap-acting device designed for switching and interlocking functions in a pneumatic control system. It may be used to feed or exhaust branch lines or to divert one or two air sources to a single device. These relays should be used only where a positive change in signal pressure occurs, such as main air in summer-winter or day-night changeover type systems, or with a two-position pneumatic signal. These non-adjustable relays come in single-pole double-throw and double-pole double-throw models. They are factory calibrated to switch at either 4 and 8 PSIG or 18 and 22 PSIG, depending on the model ordered. This device has a fixed 4 PSIG differential, meaning if the relay switches with an 8 PSIG signal on the S port, then it will switch back only when the signal drops to 4 PSIG on the S port. A typical application for the single-pole double-throw model is shown here on a unit ventilator. The function of the relay is to lock out the unit dampers during the night cycle while allowing the thermostat to maintain a set back temperature by cycling the heating valve and fan. The relay is actuated by the changing signal from the main air supply feeding the system. During the day cycle, with 16 PSIG air on the main, the normally open and common ports are connected, allowing the thermostat to operate the unit dampers. During the night cycle, when 25 PSIG air is applied to the main, the relay switches, thus blocking the normally open port and exhausting the air from the damper operator through the normally closed port. This closes the outside air dampers and opens the return air dampers. The double-pole, double-throw version of the non-adjustable diverting relay functions in the same manner and with the same signal inputs as the single-pole, double-throw model just discussed. This model provides the capability of switching two independent pneumatic signals at the same time, such as the summer-winter changeover application shown here. When the signal is below set point or in the summer mode, the thermostat signal to the unit dampers is blocked. The unit dampers are in the closed position to prohibit the hot outside air from being introduced into the cooling system. At the same time, the normally open number 2 port is connected to the common number 2 port, so the thermostat can cycle the normally closed cooling valve to provide cooling. When the system is switched over to the winter mode, the signal to the cooling valve is blocked, and the cooling valve is allowed to bleed down and close. At the same time, the thermostat signal is connected to the unit dampers, so it may control the heating and ventilation cycle. The only adjustment to be made on this relay is the switching adjustment. It is made here with a 5/64 hex wrench. The differential band is fixed at 4 PSIG and can be adjusted between 4 to 8 PSIG and 18 to 22 PSIG respectively. This adjustment should be made on a test bench where an adjustable air supply is available to ensure accurate changeover settings. The next device that will be discussed is the EP, or electric to pneumatic relays. These are but a few of many configurations of EP relays found in the field. EP relays are three-way, two-position, electrically activated air valves used in pneumatic control systems where the application requires switching, diverting, or interlocking functions controlled by an electric signal. The pneumatic switch is activated by a magnetic field generated by electric current flowing through the electric coil. In some models, the coil can be replaced, as in this new modular style device. Models are available in 24 volts AC or DC, 120, 208, 240, 277, and 480 volts AC, and are available in both single-pole double-throw and double-pole double-throw models. Shown here is an application of the single-pole double-throw model EP relay. In this application, the EP relay is being controlled by the auxiliary contacts on the fan starter in an air handling system. When the fan starts, the EP relay is energized. The normally closed port is connected to the common port, allowing the mixed air controller to operate the system dampers. When the fan is shut down, the EP relay is de-energized, and common port is vented to the normally open port, allowing the outside air dampers to go to the fully closed position. The double-pole double-throw application is basically the same function as the single-pole double-throw, with the addition of a pneumatic signal to control a pneumatic to electric relay which controls an exhaust fan. Main air pressure is piped to the normally closed number 2 port. When the EP relay is energized, the main air signal is connected to the common number 2 port, activating the PE switch and turning on the exhaust fan. These are some of the pneumatic to electric control relays, or PEs, available on the market. These relays are used where the conversion of a varying air signal to a positive electrical switching action is needed. A typical application for such a device may be to start and stop a unit ventilator, a fan coil motor, a unit heater, or possibly an air handling fan. Models are available with single pole double throw and double pole double throw switching contacts and come with either fixed or adjustable differentials. The switching adjustment is made by turning a thumb wheel or using a screwdriver. One of the best ways of setting up a PE switch in the field is to use a squeeze bulb and a multimeter. Set the multimeter to read voltage if the control circuit is hot. Remember, a voltage reading occurs when the switch is open and not when the switch is closed. Use the ohms range only if the control power is off or no wiring has been connected. For this example, a relay with no wiring connected is used. The ohms meter reads infinite resistance between common and normally open, with no air pressure on the signal input. Slowly raise the air pressure on the signal port until the switch makes and the meter reads 0 resistance. This is the switching pressure. Now, raise or lower the adjustment as needed and repeat the procedure until the proper switching pressure is achieved. In this application, the PE switch is utilizing a signal from a zone thermostat to control a duct-mounted strip heater to provide heat to the space when needed. The control signal is being provided by a reverse-acting thermostat, which is sequencing the zone dampers on a mixing box as well as this PE switch. On a drop in space temperature, the thermostat branch pressure will increase, closing the zone dampers to minimum flow. With a further drop in temperature, the duct heater will be activated by the pneumatic electric relay. The next device is the pneumatic reversing relay. It is used in applications where a proportional pneumatic signal needs to be reversed. The output signal is inversely proportional to the input signal. In this demonstration, note that as the pressure on the input port increases, the output pressure decreases in direct proportion. This is the reversing effect on the signal. Main air must be connected to the relay in order for it to produce the output pressures required. The reversing relay also increases the output volume of air to the final control device. The reversing relay has a bias adjustment, which can advance or retard the output to meet the needs of a particular application. In the application shown, it is necessary to utilize 2 normally closed valves to sequence heating and cooling from the action of a single direct-acting thermostat. An 8 to 13 pound spring range is utilized for both to assure proper close-off. The heating medium is steam, which requires a normally closed valve. On a rise in room temperature above set point, the room thermostat branch pressure will increase and open the normally closed chilled water valve. As the branch pressure rises, the output pressure from the reversing relay will decrease, allowing the steam valve to close. To effectively sequence these 2 devices, it is necessary to utilize a -5 pound bias. To assure that the steam valve is closed before the chilled water valve is opened, it is desirable to have the steam valve fully closed with a 7 pound branch pressure from the thermostat. To calculate the output of the reversing relay, starting with a 20 pound main air supply, add the bias setting and subtract the input pressure. The formula looks like this: 20 pounds plus the -5 pound bias minus 7 pound branch from the thermostat equals an 8 pound output from the reversing relay. This creates a 1 pound deadband between heating and cooling. A drop in thermostat branch line pressure will increase the output of the reversing relay to open the steam valve, or an increase in the thermostat branch pressure will open the chilled water valve only after the steam valve has been closed. The next group of devices are the selector relays. Selector relays come in a variety of types and styles as shown here. The new modular style selector relays can be used either in new modular control cabinets mounted on socket assemblies or individually mounted using field mount hardware like this bracket. Other styles of selectors may look more like this and be held by straps or left hanging by the tubing. The most common types of selector relays are the low select and high select relays. The low select or low pressure selector relay may be used when an application requires the comparison, selection, and transmission of the lower of two proportional input signals. In this drawing, the low select application illustrates the transmission of the lowest of the two signals. In this demonstration, notice that as input number 2 is lowered, the output pressure begins to decrease only after the pressure on input number 2 is lower than that of input number 1. Again, observe the gauges as the pressure on input number 2 is lowered. Input number 1 is at 7 pounds, and input number 2 is at 12 pounds. The output gauge reads the pressure at input number 1, or 7 pounds. As the pressure on input number 2 is lowered below 7 pounds, the output pressure begins to drop. The low select relay can also function as a volume booster. Using its volume boosting capability in an application that requires a large volume of control air to the final control devices, it will minimize system transmission lag. In this application drawing, note that main air is piped to the import rather than a varying signal as used in the low select application. The branch pressure is shown as equal to the input at S1. The output pressure of the booster relay can be advanced or retarded in relation to the input signal by adjusting the bias adjustment. This can be used for staging or sequencing purposes. The high select relay is used where the system requires the comparison, selection, and transmission of the higher of two proportional input signals. This application drawing illustrates the highest of the two inputs being transmitted as the branch output. Note the output pressure on this demonstration unit. The output pressure is tracking the input at port S2 because it's higher than the input at the S1 port. Watch the branch line pressure as the input pressure on port S1 is raised above the pressure on S2. Now the output pressure is tracking the S1 port. The next selector relay to be discussed is the multi-input high-low selector. The multi-input selector relay is designed for use in pneumatic control systems where the application requires the comparison and transmission of the highest and/or the lowest of multiple pneumatic input signals. All input signals dead end at the relay, with no signal air passing through the relay to the output ports. This relay is designed for pilot duty operation. If the output is to be used to drive an actuator or positive positioner, a volume booster relay should be used as a volume amplifying device. In this application, the relay is being used to provide temperature reset to both the hot and cold decks for a multi-zone unit. The branch pressure from each zone thermostat is fed to the selector relay. The highest and the lowest signal are then reproduced and utilized as reset signals to the hot and cold deck controllers. Using these outputs as reset signals allows the controllers to provide only enough heating or cooling to satisfy the zone with the highest demand. As the load on the system decreases, the deck temperatures may be increased or decreased as necessary to reduce energy cost. Only 4 of the 6 inputs are being used in this example. The unused ports must be jumped to an input signal if the low output is to be used. Otherwise, the low output will be 0. Take this opportunity to stop the tape and answer the questions in your study guide. You may want to review all or part of this tape before continuing on with the rest of this section. The summation relay is a proportioning device used in pneumatic control systems where the application requires the addition of 2 pneumatic signals. It also amplifies the volume of air available for the final controlled device. In this example, the input on the S1 port is 9 pounds and S2 is 4 pounds. Therefore, the branch line output equals 13 pounds. This relay also has a bias adjustment, which can advance or retard the output signal if the application requires it. The summation relay can also be used as a biasing relay, if needed, by using only the input on S1 and adjusting the bias adjustment to advance or retard the output signal. This bias application illustrates advancing the relay output signal above that of the thermostat to ensure that the hot water valve is fully closed before the thermostat branch line begins to open the chilled water valve. This application may be used in situations where it is not possible to have enough difference between the spring ranges on the control devices and a deadband condition is required between the 2 functions. The output of the biasing is calculated in this formula. Branch output is equal to the bias adjustment plus the input at S1. The averaging relay is used in the pneumatic control system where an average output of 2 input signals is needed. An averaging relay amplifies the volume of the air available at its branch line output. A bias adjustment is provided to allow the output to be advanced or retarded up to 10 psig from the true average output. In this example, the input at S1 is 12 psig, and the input at S2 is 6 psig. To calculate the output, the formula is the input at S1 is added to the input at S2. In this case, 12 plus 6 equals 18. Divide 18 by 2. 2 is the number of inputs on the device. The output should be 9 psig without any bias adjustment. The next relay is an amplifying or ratio relay. It is a proportioning device designed for use where the application requires the output to be amplified at 2-to-1 ratio. It would be advantageous to stage the heating and cooling with a deadband and use outdoor air for ventilation between stages. This can be accomplished by using the ratio relay with a -7 pound bias adjustment, as shown in the drawing. The formula for output of the ratio relay is the output is equal to the input plus the bias times 2. So, in the case of our example, the input is 10 psig with a -7 psig bias. 10 plus -7 equals 3. 3 times 2 equals a 6 psig output. This chart shows the relationship of output to input on the relay with a -7 pound bias adjustment. Note that with the 10 psig input from the thermostat, the output is 6 pounds, which is in the ventilation deadband. If the temperature in the space increases, the chilled water valve will open. But as the temperature drops, the outside air dampers begin to close. As the branch pressure at the thermostat drops below 9 psig, the dampers are fully closed and the hot water valve begins to open. A signal repeating relay is used where a pneumatic signal must be repeated precisely. An example is the signal from a pneumatic transmitter that must be transmitted over a long distance to a receiver controller or indicators at multiple locations. In addition to transmitting the signal accurately, it minimizes transmission lag by increasing the signal volume to remote devices. The primary function of this device is shown here, with an input signal being applied from a transmitter. The signal repeating relay draws power from a restricted main air supply, as does the transmitter. For additional information about transmitters, review Tape 3, Receiver Controllers and Transmitters. The relay bleeds the restricted line to accurately repeat the transmitter's signal as it passes on to the next device in the branch line. The signal repeating relay can also be used as a signal blocking relay by utilizing a positive air pressure supply at the S port. A signal pressure applied to the S port will block all pressure less than the S port pressure that is applied at the V port. If no pressure is applied to the S port, the V and B port are connected. In this application, during the winter cycle, the low limit would be connected to the controller's restricted branch line. During the summer, the 20-pound main air is applied to the S port. This signal will block the V port, which removes the low limit from the circuit. The air motion relay is used to sense suction and/or discharge pressure at a coil or fan. This allows pneumatic damper actuators and/or valves in the control system to be deactivated when the fan is turned off. The air motion relay can be piped either to the discharge side of the fan or to the suction side, but most often it is piped into both sides. The device must see a positive change in differential pressure from 0 to at least 0.15 inches of water column in order to work properly. The air motion relay operates by bleeding the signal pressure from the restricted branch line until such time as it senses a 0.15-inch water column differential on its high and low inputs. At that time, it stops bleeding and allows the signal from the controller to control the final control device. Shown here is the Robert Shaw enthalpy selector relay. It is a pneumatically operated energy conservation system designed for optimization of outside and return air usage in air handling systems. The enthalpy selector measures the total heat content of both supply and return air in the system and provides automatic two-position switching action to provide the proper sequence of operation to the dampers. Illustrated here is the enthalpy selector system, utilizing enthalpy transmitters in both the return and outside airstream. The output of the two transmitters is compared by a signal comparison diverting relay. The two inputs are compared. If the return air enthalpy is higher than that of the outside air, the return air dampers are closed, and the outside air dampers are opened for free cooling. The transmitters are factory calibrated and should need no adjustments at the time of installation. However, the alignment of the transmitters can be checked by comparing the output of each transmitter. The unit is shipped with both transmitters mounted in the return air mounting box to facilitate the alignment process. After alignment, the outside air transmitter is removed and mounted in the outside air duct. To align the transmitters, the unit should be mounted in the return air duct of an operating system for at least 2 hours in order to stabilize it. Connect a receiver gauge to the outside air port and then to the return air port. Both devices should have the same output. After checking the alignment of the transmitters, remove the outside air transmitter and install it in the outside air transmitter mounting box. The calibration and alignment of the transmitter should be checked at least once a year. Complete calibration instructions and a psychrometric chart can be found on the enthalpy selector data sheet. For further instruction on transmitter calibration, review Tape 3, Receiver Controllers and Transmitters. The integral reset relay is a modulating device and is used in conjunction with a proportional controller in applications where it is necessary to maintain the value of a controlled variable within closed tolerances. The integral relay adds integral action to the proportional output of a controller to minimize or eliminate the inherent offset of proportional-only controllers, such as receiver controllers or thermostats. Offset can be described as the difference in value between set point and control point of a controlled variable. This offset is caused by load changes in the controlled variable and the corresponding limited output pressure change of the controller. The output pressure of a proportional-only controller changes directly with offset. The rate at which its output pressure changes is dictated by the throttling range, as shown here in this chart. A review of throttling range and sensitivity can be found in Section 3, Controllers. When integral action is added to proportional control, the result is proportional plus integral control, called PI control or automatic reset. The integral relay is designed to overreact to the offset of a controlled variable. As the proportional controller senses a change in the controlled medium, it changes its branch line output pressure proportionally. The integral relay is factory calibrated to look for a 9 psig signal from the controller it is monitoring. As the branch line pressure of the controller drops below 9 psig, the integral relay decreases its output and continues decreasing its output until the branch line pressure of the proportional controller returns to 9 psig. At that point, the integral relay holds its output pressure steady until a load change in the controlled variable causes the branch pressure of the proportional controller to change above or below 9 psig. A typical piping scheme for the integral relay is shown here. In this case, a receiver controller is used as a proportional controller and a temperature transmitter to monitor the controlled variable. The branch output of the receiver controller is piped to the S1 port of the integral relay, and the branch output of the relay is piped to the final control device. Connected to port S2 is the timing tank. Main air is supplied to the import. The timing tank functions as a reservoir that is used to provide an air reserve to provide the timing effect within the relay. The integral relay incorporates a timing adjustment. This adjustment sets the interval at which the relay looks at the controller's output. This time setting directly affects the response time of the relay to changes in the mechanical and controlled systems to which it is applied. The slower the response time of the system to corrective action, the longer the repeat time setting needs to be. If a system is undersized, it will take it longer to recover from a load change. Therefore, the timing of the integral relay should be set to a longer interval. If the integral relay is set too fast, it will overshoot its set point in both directions. These oscillations are called hunting. Hunting can also be caused by a throttling range that is set too narrow. When determining the optimum throttling range for a controller and the timing adjustment for the associated integral relay, some judgment and experimentation will be required. Always set a controller's throttling range wide enough to prevent cycling under any load condition. A control loop is least stable under a light load or when the lag time of the process being controlled is short. A rule of thumb for setting up a controller is the throttling range should be approximately 50% greater than normal when the integral relay is to be used. The next device to be discussed is the gradual switch. The gradual switch is designed to allow the manual setting of a signal pressure from 0 up to main air pressure. Gradual switches are used where the application requires remote positioning of final control devices, remote control point adjustment of receiver controllers, or any other application where the manual setting of a pressure signal is desired. Shown here is a gradual switch being used as a remote set point adjustment for a receiver controller. The gradual switch has a range of 20 pounds and provides an output pressure from 0 to 20 pounds, or main air pressure. Another type of gradual switch is the minimum position switch. It incorporates a high-pressure selector relay in the unit. The minimum position switch is primarily used to provide a minimum position operation for damper actuators. There are two models available with 5-pound and 10-pound output spans respectively. This span can be set at any point in the range up to main air pressure. For example, the 5-pound span model could be set up to operate between 10 and 15 psig, or maybe 8 to 13 psig, depending on system needs. In this illustration, the branch line signal from the mixed air controller is piped to the S1 port, and main air is piped to the M port. The output of the minimum position switch is connected to the damper actuators. In this example, the actuators have a spring range of 4 to 8 psig. It is necessary to adjust the minimum position switch to start at 4 psig. With no pressure on the S1 port, turn the dial until an output pressure of 4 pounds is achieved on the B port. Loosen the 3/32 hex screw on the knob. Rotate the knob counterclockwise until the knob rests on its stop, and tighten the hex screw. Now we can set the minimum position switch to maintain a 5-pound minimum signal on the dampers, which will provide the minimum amount of outside air for ventilation purposes. Anytime the signal at S1 port is greater than 5 pounds, it is transmitted to the actuators to cycle them between the minimum and the full open position. Dial plates are available for all the gradual switches. They come with a variety of markings. For instance, warmer, with an arrow pointing the direction to turn the knob, or increase, with an arrow pointing the direction for increase, or perhaps one indicating 0 to 20 pounds. Selector switches come in 3 types, and each type has 2 styles. The 3 basic types are 2, 3, and 4 position switches. These devices have either a 4 or 5 port arrangement. The 2 styles of each type either block or exhaust the unused ports. The selector switches are adaptable to a wide variety of applications in pneumatic control systems. They are normally used to perform diverting functions, provide pressures, or exhaust pressures to operate final control components. Dial plates are available for each of the 4 types of switches and come in a variety of markings. The pneumatic step controller is used where a proportional pneumatic signal is to be converted to a sequenced electrical switching action. The unit consists of a series of single-pole double-throw switches actuated by a pressure signal applied to a diaphragm. Each switch is field adjustable to the full range of the control signal of 0 to 20 psig. This allows the switching action of each switch to be staged. This makes the unit adaptable to controlling air duct strip heaters, refrigeration compressor unloaders, sequencing fans, or pumps, as well as other uses. To set a switch, first apply the desired switching pressure to the diaphragm. Then turn the adjustment on the appropriate switch until it is activated. Repeat this procedure for each switch to be used in the controller. The pneumatic step controller can be ordered in standard configurations of 4, 6, 8, 10, or 12 single-pole double-throw switches. The differential pressure switch is a very sensitive pressure-activated device for sensing the operation of fans and blowers. It is also used to sense static pressure drop across filters to actuate an alarm indicating when they are dirty. The differential pressure switch operates at very low pressures. It operates in the 0.05 to 12 inches of water column range and activates a single-pole double-throw switch. This pressure switch can be adjusted to activate at any pressure throughout its range by turning the adjustment screw. The device has 2 pressure input ports, a high and a low. When sensing a positive pressure only, the high port needs to be connected to a sampling tube, leaving the low port open to atmosphere. When monitoring filters to initiate a dirty filter alarm, the high port is piped on the upstream side of the filter, and the low side is piped to the downstream side of the filters. This concludes the material for Section 5, Relays and Switches. Take this opportunity to answer the questions on this section in your study guide. You may want to review some or all of the material in this section before proceeding with the questions. For more information about the devices discussed here, or other tapes covering Robert Shaw controls, contact your local Robert Shaw Uniline wholesaler, or write to us here at Robert Shaw Controls Company, Uniline Division, Post Office Box 2000, Corona, California, 91718, 2000, the Energy Control Company.